Well, in today's videos, we will discuss some analytic geometry in space, which will be essential for our later discussions. But before starting, I owe you an apology. For technical reasons, we had a problem with voice recording last time, but the last 10 minutes were pure calculations, so I hope it will be no problem. Okay. Now, for this section, I will assume a good knowledge of plane and the Cartesian plane and straight lines, slopes, etc., line equations, and so on. So familiarity with the Cartesian plane R2, okay, is assumed. So I will not repeat those. Now in 3 space, we have direct generalizations from the plane, but also there are some specific features of the 3 space. So how do we define the Cartesian 3 space? Well, as in the previous case, we have a plane, okay, and we have a vertical angle between them. Of course, when you show 3-dimensional things in 2 dimensions, you have to distort the figure a little bit. And then we add to it a third axis called the z-axis. Now, in this formulation, it should be noted that these letters x, y, z show the increasing direction all the time. So, if for x, at this point we have 0, here we have 1, and so on. Here we have 1, and here we have 1. So, how do we show points in here? Well, we have some x value, could be positive or negative. Okay. And we move to this x value first. And then we move parallel to the y value, which could be somewhere here. Okay. And then we move parallel to the z-axis up to this point. Okay. Of course, these dotted lines are parallel, and we reach the point which we call as P, which is x, y, z. Of course, all the operations are vertical in this process. So we move vertically here, and we move vertically here. So in this sense, okay, x, y, z triple represents the point P. So we mainly added one more dimension to the Cartesian plane. Formally, okay, R3 is the set of triples where X, Y, and Z belong to R. Okay. This is not a set, but it's an ordered triple. So, okay, for example, X, Y, Z, and okay, Y, X, Z are different. Since these are ordered pairs or triples. Okay. As in the Cartesian plane, distance between 2 points in space plays a very important role. So, well, maybe, right. Before that, let me tell you that in this configuration of the positive X direction, the positive Y direction, and the positive Z direction, okay, we always observe the right-hand rule. So, in determining the directions of increasing X, Y, Z, okay, we adopt the right-hand rule. The left-hand rule could have been adopted, and it would be consistent in itself. But, okay, we need just one definition, so we had to choose one of them. And as expected, the majority wins, and the right-hand rule prevails. What is the right-hand rule? It means the following, okay? We have the x-axis, we have the y-axis, and the z-axis, meaning if we have our right-hand rule, okay, and this shows the x-axis, and if we move our 4 fingers towards the y-axis, our thumb shows the increasing z direction. Okay. Well, of course, apart from that, sometimes in showing the axes, called the coordinate axes, we will simply call them x-axis, y-axis, and z-axis, we can rotate this figure, but not change the right-hand rule. So, one also uses, okay, in showing the axes, whenever appropriate, okay, the rotated forms. That means, okay, we can rotate it without changing the order and get something as follows. This is the x-axis, this is the y-axis, this is the z-axis. Okay, all are, of course, perpendicular. Now, this still obeys the right-hand rule. When you move your 4 fingers from the x-axis towards y-axis, your thumb shows the increasing z direction. Okay. So we will, depending on the view, we will be using either way of showing it. Now the distance properties. Well, this is a very simple observation. Okay, think of, okay. Two points in space, say P1 and then P2. Drop perpendiculars, okay, depending on, okay, they can change. And these are perpendiculars to the xy plane. Now, this distance, call it d1. In a parallel way, it means this. Will be perpendicular to this vertical axis. And, of course, d is the distance between P1 and P2. So what we are after is to calculate this distance. We note that if P1 is x1, y1, and z1, and P2 is x2, y2, z2, then, okay, let us consider these 2 points. These are, say, Q1 and Q2. Then Q1 is the direct projection parallel to z onto the xy plane of the point P1. So it is x1, x2, and 0. And Q2 is x2, y2, 0. So d1 is the square root of x2 minus x1 squared, y2 minus y1 squared, because it's distance in plane between Q1 and Q2. But then the distance between P1 and P2, that is d, is the, from the Pythagorean theorem, okay, the sum of the height here, the square, plus the square of d1 added and under square root. So it is then the square root of d1 squared plus the vertical distance we have here. But that vertical distance is the distance between the z coordinates. So it is nothing but z2 minus z1. So it is z2 minus z1 squared. And when you calculate all that, you get x2 minus x1 squared, y2 minus y1 squared, and z2 minus z1 squared under the root. Okay. So it is a direct generalization of the two-dimensional distance. Well, let us apply this knowledge in one example, rather 2 examples. Okay, let us show that okay, the triangle with vertices at the points P1, that is 1, 2, 3, P2, that is 0, 1, 2, and P3, that is minus 1, 3, 4, is a right triangle. Okay, And that means one of the angles is pi over 2, or that it obeys the Pythagorean theorem. Well, these are points in space. We don't have to show them directly, but we have to calculate the distances between them. So the distance between P1 and P2, well, let me show it this way. This would be, let me take the squares so that I don't have to use the square root. So that would be the difference squared in all components. Okay. And that would be, did I write it in a wrong way? Right. So that is 3. I will calculate the distance between P1 and P3. Okay, that's these two. The differences would be 1 plus 1 squared, okay, 2 minus 3 squared, and finally 3 minus 4 squared. And this is 1, 1, and 4, so that is 6. And finally, the remaining distance between P2 and P3. That would be 0 plus 1 squared and 1 minus 3 squared and 2 minus 4 squared. That means 4 here, and 1 here, so that's 9. This says that the sides squared gives us the Pythagorean theorem. Okay. So, okay, the length squares of two side squares of the two side lengths add up to the third one. So by Pythagorean theorem, it's a right triangle. Now, as a second example, let us consider to find the midpoint of the line segment joining the point P1, that is 1, 0, 3, to P2, that is 2, 1, 1. 2, 1, 2. Okay. Now, what we mean by the midpoint? Well, we have a line segment. The point at the middle is the midpoint. Well, we recall from plane that if we have 2 points, P1 and P2, connect them and consider the point C at the middle. That is, these are of equal length. Then, okay, let us give some coordinates to these things. Say P1 is x1, y1, P2 is x2, y2, and C is, say, AB. Then this would be our A, this would be our B, and this would be our x1, this would be x2, etc. We note that the two triangles, the two shaded triangles, okay, are similar. Okay, which means that corresponding angles are equal. Okay. By elementary geometry, by parallelity, you immediately see that. In fact, they are congruent. That is, angles and side lengths are the same. Okay. Now, because all side lengths are equal, this tells us, for example, that this bottom lengths are equal, so A minus x1, okay, is the same as x2 minus A. Similarly, for the vertical parts, we have y2 minus b is the same as b minus y1, which says that A is the average, b is the average of the coordinates in question. Now, I will not do that, but adding a third component does not change the elementary geometry. And so, again, similarly, in R3, okay, the midpoint, okay, has z coordinate, which we showed as C, okay, would be z1 plus z2 over 2. Okay. So the rest is trivial. So C, in our example, becomes the average of these points. So it is 1 plus 2 over 2, and 0 plus 1 over 2, and 3 plus 2 over 2. Now, the concept of vectors is a very important tool in dealing with R2 also, but especially in space and in higher dimensions, which we will not use in this course, but generalizations will be obvious. So, let us talk about now vectors. What is a vector? Well, in physics, they are quantities which are like arrows. They have lengths and they have a direction. We are familiar with these descriptions. But in mathematics, we need to make more precise definitions. Here I will give you a restricted formulation, but those of you who will take in the second year or so linear algebra courses will learn more about vectors. Well, mathematically, any element of R2, R3, okay, or Rn is called a vector. Okay. In general, elements of R are also called vectors, but I will call them scalars here to distinguish from vectors that we will be using. So if you want, they are ordered pairs or triples, depending on whether you are in R2 or R3. Well, when we have vectors, that's elements of R2 or R3, okay, we can define operations of them. Okay. We will be showing them in R3. Well, these are basically two operations. One of them is the sum of two vectors. One comment here. In mathematics, we usually don't put arrows on top of them. Okay? Sometimes they are shown in bold letters, but whenever it's understood, it's fine. So I may be forgetting arrows now and then. Actually, I will choose not to use arrows all the time, but it will be understood. But here I will put them as an initiation. This is a definition, V1, V2, V3, plus W1, W2, W3. Okay, actually that's not the definition. Definition is here. Okay, the definition is component-wise. That is, it's V1 plus W1, V2 plus W2, V3 plus W3. And a scalar times a vector is defined as, again, component-wise, lambda V1, lambda V2, lambda V3. Okay. Well, here we have some special cases. Let me check that directly as an example, or rather a definition. Okay, the vectors I, 1, 0, 0, J, 0, 1, 0, and K, 0, 0, 1 are called unit coordinate vectors. And the reason for this will be clear in a minute. Because we have the equality that, okay, for every vector, okay, one has, the vector is v1, the I vector, v2, the j vector, and v3, the k vector. So any vector in 3 space can be written as a sum of multiples of the ijk vectors. So this makes them very special. They are called the coordinate vectors. Why are they called unit vectors? Well, let me define that in a minute. For vectors, just like the absolute value for real numbers, we have a length concept. So, okay, for, okay, V, a vector, as I said, I will be doing this for 3 space, but it's also true in 2 space. We define the length, also called magnitude or norm, by the square root of the sum of the squares of the components. Well, this, of course, is the distance between the vector v and the 0 vector. Well, the 0 vector is the one with all zeros. Okay. And if the length of a vector is 1, then it is called a unit vector. Okay. I, j, k are unit vectors. Well, sometimes in many texts, one uses, instead of double bars, one just uses single bars, just like the absolute value, but it is not the absolute value. So I will emphasize this fact whenever I use a vector. I will be using double bars. It will mean the same thing, that is this one, same as this magnitude. Okay. Okay, now this being the general set of definitions, let us now discuss how to show vectors in 3 space. That is, well, here, of course, we have the simple direct thing as, since vectors are points in R3, it's a single point. Okay. Well, for applications, especially in physics, this is usually not sufficient. So we adopt a few different ways of showing vectors. Okay. So firstly, okay, we show a vector as the following. Okay. This is the point. Okay. Okay, let me use here v1, v2, v3. This is the point. It is the vector, mathematically speaking. But of course, as we did before, and so these are all parallel, we move up to v1 and then to this point and then up and get this point. Okay. We then connect this endpoint to the origin and call this the vector v. Okay. Note that it's completely determined by v1, v2, v3. And all the operations are done that way. Okay. So if this is the point O, which is 0, 0, 0, okay, we want to show the starting point and the end point. We want to emphasize that. Okay? But for that, okay, let us define an arbitrary way of showing a vector. This is the standard way, thinking these as points in R3. But one also, okay, considers, okay, the following vectors, starting from a point A, going to a point B. Now, this should be a vector, okay, because such things are very useful in applications. We will call this the vector AB. So we define the vector AB as B minus A. Now, this will help us in showing addition and other operations on the Cartesian space or plane. Okay. This is a very useful definition. Hence, it says that OP, where P is this point, say, whatever, this is nothing but phi. Well, because of, again, applications of vectors, this vector, it's the same as P, but once you show it this way, you call it a position vector. Just because of the applications. We will be using this definition quite a lot. In fact, it says that, okay, if I show B minus A somewhere here, okay, it says that the AB vector here, this arrow, is parallel to, okay, the point B minus A vector, starting from O. In this sense, we identify. Okay. Thus, AB is identified with the vector B minus A. Okay. As I said here, if you show the point B minus A on this space, okay, and connect it to the origin, you get parallel arrows in the same direction with the same length. And so this is an identification with B minus A. Right, in this sense, okay, how can we show the addition process in space or plane for vectors? Okay, I will write these things in plane because after all, even in space, all this process takes place on a plane. Not the xy plane, but some plane. So I will consider it in plane. The case in space is exactly the same. Okay, this would be shown in plane. Well, how can we show addition now? Suppose we have 2 points, okay, A and B. Well, thinking as vectors, we said we would connect them to the origin. So we have 2 vectors, the vector A and the vector B. Okay. Now, construct a parallelogram. Okay, that means the sides are parallel and the lengths are equal. You find a point D. Okay, now what is this D? Okay, that is actually the following. Let us look at the vector AD. Okay, the vector AD is D minus A. Okay. And if I add this to the vector B, okay, actually I subtract B from it. No, let me see. AD is D minus A, that's right. Well, okay. So also by parallelity, AD is the same as B. We said that we will identify them, they are parallel, and they show AD has the direction the same as B. It's parallel and its length is the same, so we identify them. Well, then of course, this says that, okay, B is actually D minus A, or D is A plus B. So, adding 2 vectors A and B means, okay, forming the vector OD. So OD is the sum of the 2 vectors according to our original definitions. But then, okay, this means geometrically we move B parallel in a way so that its starting point, the origin, starts from A. So geometrically, we identify B with the vector AD. Okay. So geometrically, okay, we add, or rather, we translate, okay, in a parallel way, B to AD. Okay. This means that the endpoint of A becomes the starting point of B. Thus, if we have two arrows, 0 to A and A to D, it means the sum. Okay. Because it's a parallelogram, the lengths are all equal, so it obeys our definitions so far. Now, the geometry of addition is this. Of course, one can discuss other aspects. For example, given a vector, what is the negative of it? Or what is 1/2 of it? Okay. So similarly, okay, given a vector A, okay, then negative A becomes minus A1 and minus A2 according to our definition. But geometrically, this means, okay, it is the vector which is parallel to A, but in the opposite direction. Of course, the lengths don't change. Similarly, okay, or if we consider 1/2 A, this would be 1/2 A1, 1/2 A2, same in space. Okay, so it is in the same direction, but its length is 1/2 that of A. That by direct calculation, one can see that. Actually, it's true for all scalars.